Welcome to the session on integration, solving differential equations. The objectives for this session are to solve differential equations. We can use integration to solve differential equations. We will solve first-order differential equations by separating the variables. This we can do, for example, when dy dx equals f of x times g of y. We can write this as the integral of 1 over g of y dy equals the integral of f of x dx. The solution to a differential equation will be a function. When integrating to solve a differential equation, we still need to include a constant of integration to give the general solution to the differential equation. This will represent a family of solutions, all with different constants, whilst also satisfying the original differential equation. Let's take a look at an example of a general solution. We're going to consider the first order differential equation dy dx equals 6x squared minus 3. If we integrate this, we find the general solution, which is y equals 2x cubed minus 3x plus c. This represents a family of solutions. Here are some particular solutions. So when c equals 1, we have y equals 2x cubed minus 3x plus 1. When c equals 0, we have y equals 2x cubed minus 3x. And when c equals minus 2, we have y equals 2x cubed minus 3x minus 2. All these curves, plus infinitely many more, depending on the value of c, gives us a family of solutions. Let's take a look at an example of how to find the general solution. We're going to try and find the general solution to cos x squared dy dx equals y squared times sine squared x, and we're required to give our answer in the form y equals f of x. So let's solve this. Here's our equation again. Let's rearrange this. We can write this, if we divide through by cos squared x, as dy dx equals y squared times tan squared x. And then we can rearrange this so that all the y's are on one side and all the x's are on the other. We're going to do this by multiplying, in inverted commas, through by dx and dividing through by y squared. And then we integrate. A more integrable form of tan squared x is sec squared x minus 1. This can also be linked back to our theory. Let's now integrate. So we have the integral of y to the minus 2 becomes minus y to the minus 1. And the integral of sec squared x minus 1 becomes tan x minus x. And of course we have our constant of integration, c. If we rearrange this, we have y equals minus 1 over tan x minus x plus c. And this is the general solution to our differential equation. Now let's take a look at another example. We're required to find the particular solution to the differential equation on your screen, with boundary conditions y equals 6 at x equals 0.5. So let's solve this. Again, we're going to rearrange this. First refactorize. And then we divide through by 1 minus x squared. And we factorize further. And we can now cancel. And notice again, dy dx is in the form f of x times g of y. And we can use the formula or first principles to get to the same arrangement. So notice here we've divided through by y to get the y's all on one side. And then we integrate. And again, let's link back to our theory. And now we can start to integrate. So we have the integral of 1 over y dy is equal to ln y. And the integral of 1 over 1 minus x is minus ln of 1 minus x. And then we have the constant of integration. Here we're going to use ln c rather than just c, because this will help us manipulate the equation later. Let's now rearrange. In particular, we've rearranged minus 1 ln of 1 minus x to become ln of 1 minus x to the power minus 1. Everything else remains the same. And now, using the rule ln AB equals ln A plus ln B, we can rewrite the first expression as ln of c over 1 minus x. And so now, of course, we have y equals c over 1 minus x. We've simply removed the ln from both sides, or raised both sides to the power e. And so we have a general solution, y equals c over 1 minus x. We now proceed to find the value of c, because we have the boundary conditions. And in order to find this particular solution, we know that when x equals 0.5, we have y equals 6. So plugging in the value y equals 6 and the value x equals 0.5, gives us 6 equals 2c. And rearranging this gives us c equals 3, or dividing through by 2. And therefore we have, plugging in c equals 3, that y equals 3 over 1 minus x. This brings us to the end of this session. If you have understood the content of this session, you should be able to solve simple differential equations. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.